Suppose we have n independent normal random variables, x1, x2, up to xn. Each xi has its own mean mu I and variance sigma I squared. We form their sum w equals x1 plus x2 plus plus xn. The question is, what distribution does w follow? Here are three example Gaussians, x1 in blue, x2 in green, x3 in purple. It turns out w is also normally distributed, with mean equal to the sum of all the individual means and variance equal to the sum of all the individual variances. We will prove this in one clean argument using moment-generating functions. The key insight is the multiplicative property of moment-generating functions. The MGF of w is the expected value of e to the sw. Substituting w as the sum of the xi gives the expected value of e to sx1 times e to sx2 all the way to e to sxn. Because the xi are independent, the expectation of a product equals the product of the expectations. So the MGF of w is simply the product of the individual MGFs, phi x1 times phi x2 times phi xn. This is the entire logic of the proof. For n equals 2 as a concrete check, the exponents add together directly. Now substitute the known MGF of each Gaussian. For xi following n of mu I, sigma I squared, the MGF is e to the mu is plus sigma I squared s squared over 2. The product of n such exponentials is the exponential of the sum of all the exponents. Watch how the product of exponentials collapses into a single exponential. The s terms collect to give mu 1 plus mu n, all times s. The s squared over 2 terms collect to give sigma 1 squared plus sigma n squared times s squared over 2. So the combined exponent has exactly the form of a Gaussian MGF. W is Gaussian with mean mu w and variance sigma w squared. QED. Look at the exponent we obtained. Compare it with the MGF of a single Gaussian, e to the mu s plus sigma squared s squared over 2. The two forms are structurally identical. The forms match when we set mu w equal to the sum of the mu I and sigma w squared equal to the sum of the sigma I squared. A distribution is uniquely determined by its MGF. Watch as we add more and more Gaussian random variables together. The combined bell broadens with each addition but stays perfectly Gaussian throughout. With 2, 3, 4, 5, 6, 7, 8, 9 components. The sum is always Gaussian, the variance growing linearly and the standard deviation growing like the square root of n. The conclusion, w equals x1 plus xn, follows a normal distribution with mean mu w equal to mu 1 plus mu n and variance sigma w squared equal to sigma 1 squared plus sigma n squared. For the special case where all xi are independent and identically distributed with mean mu and variance sigma squared, this becomes w tilde n of n mu, n sigma squared. Both the mean and the variance scale linearly with n. Watch the bell widen as n grows. This result sits at the heart of probability theory. When we standardize the i'd sum, subtract n mu and divide by sigma root n, we get a standard normal, exactly, for every n. This is not just an approximation. For Gaussians, the standardized sum is exactly normal regardless of how many terms we add. The Central Limit Theorem says that for any distribution with finite variance, the standardized sum converges to normal as n grows large. For Gaussians, convergence is immediate. Gaussians are closed under addition, and the moment-generating function makes that plain. Here is the standard normal bell, the limit that every sum of Gaussians already lives on.